Colleague Johannes, we're going to talk to you guys about a project of ours from Facebook called Getafix. So just to start, give a little motivation for this project. In recent days, there's been a lot of work in what we call the big code space, where researchers are throwing machine learning algorithms at large repositories of code. And this work has a lot of different applications. If you guys were here yesterday for the talk by some of our colleagues, you saw how this work is being used for improving the ability of developers to find code that they're searching for. But it can also be used for other things like improving auto-completion suggestions, building a model of what correct code looks like, and using that to detect bugs when code doesn't match up with that model, and even sometimes synthesizing new code based on some sort of specification. Now, these are all interesting applications, but for the most part, they just rely on looking at a static version of your repository. But that's not all we can do because, as we know, code isn't static. It changes over time. And so these code changes show us how developers extend their projects and create new features, but also how they modernize and improve existing code. And so looking at the history of a repo shows us how code evolves over time. And if there's patterns in the way that code is evolving over time, then that generally means that developers are doing some sort of repetitive and routine work. So the question for us is, can we save time for developers by automating some of that routine work? And in fact, there's several categories of routine work that we're talking about here. The first such category is routine refactorings that occur from time to time, either due to new features of language that make it easier to do something that was hard before, or simply because developers notice there's a simpler way to do something. Another category is code review, where developers sometimes make repetitive comments, which developers then address in repetitive ways, such as around preferred API usage. And one final category is bug fixing, where developers look at bug reports and fix them. So for the purposes of this talk and for our project, when we talk about bugs, we're actually going to just be talking about warnings reported by static analyzers. And so we'll use this last category of bug fixing to explain more about how Getafix works. So as you might know, one static analyzer that's used heavily at Facebook is Infer. And since we have a continuous integration environment at Facebook, it means Infer runs on all of the changes that developers submit. So we can query historical commits and see how many and of which type of different warnings were reported. This also means we can simply search for code changes that get rid of bugs, such as this one right here. If we look at that specific edit, we can see what the developer did to get rid of the bug. In this case, they've removed a potential null pointer exception by adding a condition that guards dereference of the variable v. And in case anyone's wondering why null pointer exceptions are still a thing, at Facebook, the Android app is written in pure Java, and still null pointers account for quite a lot of production crashes, so this is still very relevant, sadly. So now imagine we take thousands of the bug fixing edits that developers make to address null pointer fixes. As you might expect, turns out there's a wide variety of ways that developers fix these single kind of warning. And it might be possible to handwrite a couple of rules, but really there's such a large variety of different ways that this isn't really practical. What's interesting here, though, is that the fixes that we're showing here are not actually training data that we used to learn patterns, but rather these are anonymized versions of fixes that we actually suggested and that developers accepted at Facebook and merged into the repository. So what do these fix suggestions look like to developers? Well, previously, Infer would have posted a warning in our code review tool, leaving a comment on the line that it believes to be problematic. And now we show the same message as before, but we also have a fix suggestion that can be accepted or rejected at the click of a button. So now we'll go through some more details of how we generate one of these fix suggestions to show you how Getafix works. So the process of creating fix suggestions is basically 3 steps. To start, start, we're going to take raw human code changes at the textual level, and we'll turn them into small AST edits. Secondly, we'll mine patterns out of those AST edits. And then third, we'll apply the patterns learned in the second step to new bugs, generate potentially a large number of possible candidate fixes, and we'll rank them based on how likely we think that a human would have made such a fix. So to start, we'll turn the human changes into AST edits. Cool. And as I mentioned before, we'll focus on changes which fix bugs. So changes are any sort of change is a change to a file, but for our purposes, we'll actually get the entire file before and after the change. Once we have a file pair, we'll parse both the before and the after to a generic AST representation. This generic representation has like a string label and value for each node, as well as some information about the relationship between children and parents. And since we use this generic representation, it allows us to be actually agnostic to any sort of language, so we can extend this to any language for which you can parse to an AST. And so once we have our before and after ASTs, we'll then run a tree differencing algorithm between them to tell us what changed. And this tree differencing algorithm will try and find mappings between nodes in the before and after, which it thinks are the same, and then we'll use that information to say what it thinks it changed. So perhaps in this case, the tree differencer thinks that the node marked in the orange color had its value updated, the node in red was removed, and the two nodes in green were inserted. And there's a fourth type of modification. Nodes can actually be moved as well, or subtrees can be moved, but we didn't show that here just for simplicity. And if anyone's curious, we use a variant of the gum tree algorithm to do this tree diffing. So now that we've identified which nodes were modified, we want to create small AST edits showing what changed. And so we want to look for nodes that, according to the tree differencer, were maps to one another. And we'll take the subtree rooted at each of those nodes in the before and after and create an edit from them. And the reason that we want small localized edits is that we want to be able to learn patterns from pieces of developer changes as opposed to comparing entire potentially large changes all at once, since it's possible that someone might have done something in addition to fixing a bug in the change that they submitted. So, for example, in this case, the two nodes which are marked as updated are mapped to one another. So we'll create an edit which just contains the updated nodes. Similarly, the parents of the updated nodes are mapped to one another. So we'll create an edit from them as well. Note that this edit includes both the updated node as well as inserted nodes. Similarly, the parent of the node which was marked as deleted is mapped to a node in the after, so we'll create an edit from those as well. And the parent of those parents are mapped to one another as well, so you sort of get the idea. We're just going to do this for all of the nodes which, according to the tree differencer, are mapped to one another, and for which there's at least one modified descendant. And so we'll do this for each of the file pairs in our initial training set, and we'll create a large data set of human AST edits. Cool. Now the second step in our process is we're going to look for patterns in these AST edits. Cool. So to do that, we're going to look at all of the edits and determine which pair of edits is most similar according to a heuristic which I'll explain shortly. Let's say in this example, our heuristic picks these two edits right here. Edit A happens to be the fix we saw before, where the variable v is being protected from a nullity reference with a conditional check, and edit B is structurally identical, except we're using a different variable and method name. Now we're going to calculate a pattern from these two edits, which preserves as much information as possible. Since the structure of both of the edits agree, we're going to maintain that structure, and similarly, since both edits use the null and zero literals, we'll maintain those as well. However, in the locations where they differ, we'll use abstract metavariables, in this case h0 and h1. Sometimes we like to refer to these as holes. And then we'll repeat this process on and on, repeatedly searching for the most similar pair of edits or possibly already abstracted versions of edits. And we'll stop when we get to a point when the most similar pair that could be merged is so different that it doesn't make sense to, according to some of our heuristics. So you could imagine, for example, an edit which inserts a conditional null check, attempting to merge with an edit which deletes a return statement. There's really nothing in common with them, so merging them doesn't give us any information, so we stop merging. And so when we're done, we'll end up with this forest of hierarchies here, where at the leaves you have the original human edits, and then further up, the higher you go in the hierarchies, you get more and more abstract patterns. So let's talk briefly about the scalability of this approach. The hierarchical clustering that we're doing here is at best an n-squared algorithm, possibly n-cubed depending on your implementation you use. And so given the large quantities of data that we're working with, this sometimes doesn't scale. Like in some instances, we were looking at potentially days to finish, which isn't good enough. So we found a way to speed things up. Note that in this forest of hierarchies, any two separate trees that you have, if you look at the raw original human edits that you started with, you never actually have to compare edits from two different hierarchy trees in order to get the result that you end up with here. So if we can partition the edits such that two edits in different partitions are guaranteed to end up in separate hierarchy trees, well, then we can just greatly reduce the size of n in our n-squared algorithm. So the partitioning function we end up using relies somewhat on our properties of how we merge edits and decide when to stop merging. So I won't go into too much detail about it. All you need to know is we take the number of modified nodes at each level, so the number of colored nodes at each level in the before and the after tree, and turn that into a hash. So here, for example, there's one modified node at level 2 in the before, one modified node at level 2 in the after, and two modified nodes at level 3. So we'll turn that into some sort of hash. We'll compute one of these hashes for each of the original edits that we're starting with, and then partition based on those hashes, and then we'll perform hierarchical clustering independently on each of these partitions. Cool. So what does one of these forest of hierarchy trees look like in practice? Well, this is an example from 1 month of changes to the Android app at Facebook. It's a really large hierarchy tree, as you can imagine, because there's a lot of changes happening at Facebook. So this is really zoomed out, but even at a zoomed out level, you can see a little bit of what's going on. So nodes marked in blue/purple color correspond to nodes being moved. And so on the left, we can see there's a bunch of nodes being moved, which turns out correspond to some refactorings. Possibly the most interesting part of this image is in the middle, where there's a large red and green section. This actually corresponds to an onboarding task for new engineers at Facebook, where you basically take a large structured fragment of code that's very similar and just change a couple pieces, like change a string to be your name, for example. And so then, of course, to practice using source control and the code review tool, you're asked to commit your change and then delete it afterwards. So that's why you have a really large edit, which happens a bunch of times, being inserted and deleted. And then finally, there's a long tail of spurious one-off changes, potential bug fixes, and other stuff. All right. So the hierarchical clustering process is great, but we sort of glossed our way past one of the most important parts, how we determine which two edits are most similar. And it turns out we do this based on this abstraction that we create. And at a high level, we prefer abstractions which are less abstract. We want to maintain as much information as possible, as long as possible. So, of course, then the question is, where do we create this abstraction? And it turns out the answer is, it's a process called Anti-Unification, which is essentially the opposite of unification. Given multiple input trees, we'll return a single tree which maintains as much structure as possible. And in any location where the input trees differ, we'll replace them in our abstract representation with some sort of meta variable or whole. And of course, you can retrieve the original trees you started with by substituting subtrees into each of these meta variables. So given two of our AST edits, the way that we'll use this approach for them to create a generalization is first we'll anti-unify the before trees, and then we'll anti-unify the after trees. But something that's important is that we'll try and reuse any substitutions that were used when processing the before trees while we process the after trees. So to make this a little more concrete, we can go through an example here. Here we have two edits which each conditionally return 0 if the variable in question is null. At the AST level, the first edit looks like this, MC referring to method call. And the second edit looks very similar, but A and B are replaced with C and D everywhere. So as I said, we'll start by processing the before trees together. So the way that we'll do this approach is we'll do a depth first search, and for every node that's the same, we'll include that in our hierarchy, or in our abstract representation. And once we hit different nodes, then we'll stop at that point and make meta variables there. So going from the roots, the block nodes are the same, so we'll keep that around in our final representation. Method call names are the same as well. However, when we get to A and C, these nodes have different values, so we have to make a substitution here. So we'll call it H0, and remember that it corresponds to A in the first edit and C in the second edit. We'll continue along. Now we again hit two nodes which differ, so we'll create another substitution here. And remember that H1 corresponds to B in the first tree and D in the second. Now we'll continue to the after trees, and as I said before, we'll bring along the substitutions that we already have made. We'll do our depth first search, continuing along until we hit two nodes which differ. And now here, we realize we want to create a substitution which refers to A in the first tree and C in the second. And we realize we already have H0, which does exactly what we want to do. So we'll actually just go ahead and reuse it. Then we'll continue along until, once again, we hit two nodes which differ. Once again, here we can reuse H0, so we'll do that. And continuing along, now we have B and D, which corresponds to H1, so we'll use that. And then we'll finish without having to make any more substitutions. So if we pair up the result of anti-unifying the before trees from earlier with the result of anti-unifying the after trees, we now have a single templated edit pattern which represents both of the original edits that we start with. And now we can generate candidate fixes by looking for places where the before matches into a buggy AST and then just mutating it into the after and writing out the source code changes. Cool. And anywhere where we have these holes in the before, this can just match with any sort of node. All right. And here's the easier to read source code representation of the abstract edit that we just found. As mentioned earlier, we find a wide variety of edit patterns for fixing NPEs. So here's a couple other examples. And so when we use these patterns to generate fixes, we generate potentially a really large number of fixes. And so I'll hand it to Johannes here to talk more about how we decide to prioritize which of those fixes to show to developers.
Thanks, Andrew. Yeah, I'm Johannes, and you've seen now how Getafix learns patterns, and I'll dive into how it uses them to fix new, previously unseen instances of certain bug types. So whenever Getafix is asked to fix a new bug B, it applies all patterns it learned for that bug type and creates a potentially massive list of fixed candidates. So if you think of the hierarchy you've seen previously, even the blue nodes down there, which corresponded to the original human edits, we even try applying those, right? Because if we happen to encounter code that looks exactly like something we've seen before, that's probably a strong signal we should also do exactly the same. So let's say one of those patterns is P, which is take a statement and just wrap it guarded by a null check, new if block. Then what are the fixed candidates? Well, you can certainly wrap both of the statements that are within the while loop individually, but you can also wrap the entire while loop, and we count that as a match in the first line, to guard the entire while block. But those are 3 fix candidates. Which one of those are actually fixes? We can, of course, rerun the tool which initially complained in the first place about B in the second line here, the null pointer exception, and see if it went away. Well, if you wrap the entire while loop with an if check, then likely infer, or whichever tool you're using, is not going to complain anymore. So that's a fix. And of course, the same is true if you just wrap the buggy statement directly. But yeah, it's not a fix to wrap the important side effect here. But that's not really satisfying yet, because what we're looking for is what a human would do. So what would a human fix look like? And in this case, I'd argue that a human would not wrap the entire while loop, because apparently there's this important side effect in it. So what Getafix has to kind of come up with is decide hfix. So let's formalize that a bit. Fix candidates are really triples, B, P, Z, or Z, meaning pattern P is applied Z lines away from bug B. And that makes match, fix, and hfix predicates of this triple, and it's those predicates that we want to decide, specifically hfix. However, they're also increasingly hard to decide, so while match is just Getafix enumerating fix candidates, which is almost free, and we enumerate thousands of them, fix requires, spending CPU cycles, because we're invoking some tool that usually can take from seconds to minutes to run and complete. And hfix is the most expensive one because it requires human resources. Only a human can ultimately decide if this looks like a human fix that they are happy to accept into their code base or not. So in practice, we want to spend those resources as carefully as possible and actually never show, decide our final predicate more than once. We only want to ever show one fix candidate to a human. If the human is unhappy, we give up. Otherwise, we spend too much human time. So we only want to show one thing. And we also want to only validate a handful of fix candidates, as otherwise we take too much CPU time. And maybe at the time where we come up with a fix candidate, it's already too late. Engineers have moved on. So we have to rank right after enumerating, and rank as good as possible to spend our resources in the best way possible. What do we want to rank by? It's this conditional probability. How likely is a fix candidate that we know to be a match also a human fix? And while we have never seen B before, we can of course model this using our training data. So B train are all the bugs that we've seen being fixed in our training data. And yeah, the question is then, what fraction of when P and Z were used, what fraction of matches, which are fix candidates, were also the human fix? So since it's our training data, we actually know hfix for once. Hfix for our training data is exactly our training data. So here it's decidable, but it would be way too slow to calculate exactly this fraction during ranking for thousands of fix candidates, and we would have to look at our training data. So we do something slightly faster and easier to interpret as well. We can factor this fraction into 3 factors, which are each, fairly easy to approximate or almost free to calculate at training time. And as I'll show with an example now, they also have an intuition attached to them. And for example, only the middle one, S location, actually depends on Z at all. So let's look at an example. Let's say we have a bug B, again, a null pointer exception, in the marked line, and we have 3 patterns that we want to create fix candidates for and rank. The first pattern you've already seen before, just use a conditional expression. The second pattern is wrapping a return statement in a null check, and the third pattern is the early return pattern, which lets you escape from function if the variable in question is null before you hit the line in question. So Getafix will create the following fix candidates from these patterns. P1 and P2 only result in a single fix candidate, whereas P3 just set, insert an early return, and that applies in 3 spots here. Even though to a human, the last one especially might not seem too smart, that's one of the candidates. And it's worth pointing out again, Getafix is purely syntactic. It has no semantic information about how programming languages work, which makes it language agnostic, but it has no clue that this last candidate of P3 is actual nonsense because the statement it inserted is unreachable. And the same is true for P2. This will probably also be a compiler bug because there is no definite return in this function anymore. It's also too expensive to invoke our validation tools, which could easily discard those two options because we want to rank before spending CPU resources. So for now, we're stuck with those. So the first factor for approximating our ranking score is as prevalence, and it's supposed to prefer patterns that have been observed more often in our training data. We have that information. We can just count while we do our pattern mining. And let's just say that 30% of the time we've seen P1 being used in our training data, 15% of the time P2, and 40% P3. Okay. Then S location, which is supposed to prefer patterns being used in the locations where we also saw them being used in the training data. And now you'll immediately see that the third candidate of P3 has score 0 because hopefully in our training data we saw no cases where the bug was fixed by inserting an early return after the bug. So that's the way it's discarded. Well, P1 is kind of an inline pattern. It's just wrapping in expression with a conditional. So let's say 90% of the time it happens exactly on the line. Similar for the wrap in an if. It's a little less because maybe in our training data we saw people also wrap more than just a single line, which counts as having more distance to the bug. And apparently we also saw in our training data that most of the time the early return happens very close to the bug, 50% of the time versus 25% of the time if it's 2 lines away from the bug already. And the last score, as specialized, is supposed to prefer patterns which are, well, more specialized, have more context. So if they match, it's probably a strong sign that they're also the right thing to do in this case. Think, for example, again of what I said earlier. If we actually use concrete human edits, which have no holes in them, and they happen to match in new code, then that's a very strong sign that we should also do it. So they would have a very high S-specialized score. And in case of the P1 candidate, let's say that 1 in 100 average AST nodes is matched by this pattern. All the pattern needs is a function call expression, which is matched by v size here. And let's say that 1 in 100 AST nodes average are function calls. So it matches fairly often. The P2 pattern requires a return statement with a function call in it, and that's obviously already more special than the first one. So let's say it happens, or it matches 1 in 200 average AST nodes. But on the other hand, the P3 pattern was the one that literally, it just says anywhere in a block, insert this new if statement. And let's say that 1 in 20 AST nodes allow you to insert the pattern or apply the pattern right there. So it's not very special. So maybe we come up with those final scores that we rank by. And luckily, the P1 candidate is ranked highest, and the ones that wouldn't even pass validation are discarded or ranked lower. All right. So you've seen now how we fix null pointer exceptions, but that's not all Getafix can do, as also Andrew already hinted in the very beginning. Learning from human code changes allows us to do way more, and I'm going to share some of the vision that we have for Getafix in the daily life of a developer. And that vision is automating routine engineering work. So what is engineering work that developers do every day? We think it's a spectrum from very boring tasks and mundane things, repetitive and so on, to exciting work like discovering new monads, writing papers, or working on new features in your program. And it is the routine work, like fixing bugs, reviewing code, and refactoring that we want to automate or at least help with Getafix. So engineers have, more time doing those interesting things. So let's look at those 3 routine things in a little more detail. We've already talked about fixing bugs. You've seen us focus on infer so far, but we also looked at Google Error Prone, which has a large variety of things that it can complain about, and we also trained Getafix on past error-prone fixes, and there's just 2 examples of things we've learned. And the question now is, how well does it work? So this is just a part of our paper. Please, there will be a pointer later. Look at the paper if you want more detail. But the way we evaluate it is, for all those different bug categories or bug types, we took a number of human bug fixes that we could find in open source projects or at Facebook. That's the examples column here. And we then, trained from those. We trained Getafix from a subset of those and reapplied what we learned to another disjoint subset of these example fixes, and saw if Getafix reproduces precisely the after part, reproduces precisely what the human did. So applying Getafix to the before, does it produce precisely, syntactically, exactly the same code as the human produced? So it does not look at semantics or anything. And what we found is that in 10% of cases, we are in fact able to precisely predict the null pointer exception fix that a human performed. And remember from earlier, Andrew showed the large variety of ways you can fix that. Maybe they're semantically identical, but we don't count that. And we have higher accuracy for the error-prone things. The top 1 accuracy column shows you how often our top-ranked candidates contains, so matches exactly the human fix, versus the top 5 accuracy column, which just says, is the human fix among our top 5 ranked fix candidates. For null pointer exceptions in particular, we've already deployed auto fixes, so showing them to our engineers at Facebook in production for, at this point, I think almost half a year. And we found that in 42% of cases, the fix that Getafix suggested was just accepted as the way people fixed the bug. And there is some evidence that our engineers are pretty picky about the code they accept, because, for example, in another 9% of cases, we saw that people did not accept, but then wrote semantically identical code. So in a real-world deployment, it's really important to get everything right. White space, if there's a white space issue, people rewrite the fix themselves, because there's no point in clicking a button if then you have to go in again manually to fix it up. So, for example, what we saw in that 9% category is if you have a conditional, if you invert the conditional condition and swap the then and else case, that's the same thing, but some people seem to be very particular about the order they want to have things, so they wrote that by hand instead of accepting our suggestion. Recall that all Getafix needs as training data is an example set of human edits. So maybe we can also do other things, and we tried other things. For example, taking the changes that are performed in response to code review as training data. So if people during code review say, hey, why don't you use this instead of that? What then happened is our training data. And we found that we essentially learn detecting and also remediating anti-patterns. So we have a way to learn lint rules in a sense now. And we did that and also deployed that already. And yet another idea one could have is what happens if we just throw Getafix at commit histories in their entirety. No filtering, no nothing, just all commits that happened. And we did that for a number of open source Java projects, represented by these commit histories here. And what came out were refactorings. These are just a few examples of the things we've seen. It's usually about using modern Java features like catch blocks with like union type exceptions, using lambdas, or using for each loops instead of regular for loops. And some of those patterns we've also deployed as lint rules now. So this is Team Getafix, Andrew, me, and our manager Satish Chandra. And yeah, please have a look at our paper, which you can find on archive, for way more information, evaluation, and so on, and technical details. This is a selection of our related work. The first paper, Learning Quick Fixes from Code Repositories, influenced us a lot. It also has the idea of using anti-unification to create abstract representations from multiple human edits The idea came from that paper. And yeah, to conclude with the takeaways, you've seen a fairly simple, purely AST-based approach to learn fixed patterns or refactorings, whatever you like. And we use that at Facebook. And despite its simplicity, it has fairly high accuracy. It's fairly good at predicting exactly human fixes. And thanks to its simplicity, it's also language agnostic. At Facebook, we already use it with Java, Hack, or PHP derivative, and Objective-C. And more generally, yeah, we'd like you to take away that while automation can't do most of a developer's work, so there is no danger, yet at least, we can at least automate a lot of the boring, mundane stuff. So why not automate that as much as possible to leave engineers more time to spend on things they really like doing. So yeah, the selection of things we presented was fixing bugs, reviewing code, and refactoring. And overall, we hope that you leave thinking that big code is not necessarily a burden, but an opportunity. Yesterday, you may have seen our talk about neural code search and aroma, which other engineers in our group gave. And yeah, big code can be noisy, but there is a lot of it. So using machine learning or statistical methods, you can build really, really helpful tools. So embrace uncertainty like Thomas Bayes would do. Thank you. Any questions? Whoa, that was fast. Maybe you were first.
I was wondering that if you apply the same fix over and over again, wouldn't you have a lot of code duplication? Like if these fixes become larger, then there would be like another core problem that you want to fix rather than having all these minor fixes which will be quickly accepted by the developer, but there is a better root cause. Or do you expect this to be like seen in code review and then fixed?
So, well, for the fixes we've done so far and also what we've presented, I think we're not scared of causing duplication so far, because, for example, the refactorings are usually actually simplifications, so there shouldn't be any duplication introduced at least. For the null pointer fixes, well, there you could argue that a real solution would be changing the language in a way that you don't even need to wrap everything, with null checks and so on. But yeah, long term, something we haven't reached yet. But if we had bigger fixes or mutations, then yes, that might be a concern.
What was the size of your training set? Did you have to select that manually, or was it like you were doing some sort of heuristic based on the comment and the size of the commit?
In case of this table right here, the error-prone things we collected manually by looking at GitHub projects, where sometimes you find commits that literally say fixing error-prone warning, whatever. And in the case of MPs, we actually, as we showed in one of the earlier slides, we can just query for changes which we saw more warnings before. We saw after the change for map that warning was fixed. And we just find all of those changes without any sort of heuristics or filtering, and just let the pattern mining approach determine what's noise and what's interesting.
So I was curious, Facebook Infer talks a lot about biobductive inference, where you do this bottom-up analysis where you take a small piece of code, infer pre and post conditions, and then you use that to calculate the analysis for the rest of the program. I was curious if you had looked into using very early analysis of these small changes to see if they fit before you do the whole program analysis. Yeah, so in one of your examples, you had a return statement, and then you had a check if this thing is null. And I would imagine that a compiler's level liveness analysis would probably catch that fairly quickly. And so I was curious if you had looked into very basic program analyses that could reject those before you even do a statistical ranking.
So far we haven't, but that's a very good point. So part of our idea, kind of our architectural goal is to be agnostic to programming languages and signal providers. So doing something like that would kind of, break the abstraction open a bit, but sure, yeah, for this particular case of fixing infer, definitely that would be faster, but haven't so far.
Apparently, you need to use the mic and repeat the question when they ask.
Okay. So the question was, have we looked into using more local, way faster analysis before invoking, for example, all of infer to more quickly discard fixed candidates that are obviously wrong according to some semantic properties? And we haven't looked at that so far, mainly because our architecture, we try to be as agnostic to programming language and tool, like infer, for example, as possible. So we have a very rigid kind of pipeline so far. Would be possible, but haven't spent the effort. Since running infer, once or twice takes a few minutes, but that's not the bottleneck usually. So that's okay. I also do have an overview of our pipeline, sort of. So, if we stick to this very rigid model where just validation is this one block, then it's way too complicated to break it open. More questions? Yeah, you can I'll repeat it.
Okay. So people in real life follow GPS into lakes, right?
Yep.
What are you doing to avoid that?
Well, we're not actively doing a lot to avoid it. I mean, the things we suggest are at least validated against the static analysis tool that complained initially. But ultimately, we have to trust the engineer. We expect them to really think about what we're suggesting there. Even though, I guess for the things we focus on so far, we would be very careful deploying something that could lead someone running into a lake. So we trust.